In this video, we're going to start talking about how to analyze merge sort. All right, so we're going to start with a claim, okay? And this is given by the textbook, so I'll just read this. Top-down merge sort uses between 1/2 n log n and n log n compares to sort any array of length n. Okay, this is our claim, coming straight from our textbook authors, Sedgwick and Wang. All right, so we know this is true. It's in the textbook. We know it's true, right? Great thing. What we're going to try and do is we're going to try and prove this claim. Although we know it's true, we don't really know how or why it's true, right? It's just a claim to us right now. We want to actually show that we want to prove to ourselves that it is correct, okay? And not just take it. So we're going to do that. Now, as kind of a general note, we don't usually get to do this, right? So if I want to prove that something is a certain way, I don't get to start with the result and then try to prove the result, right? If I have an algorithm, I'll have this idea of, oh, hey, so let's say I have an algorithm. I want to know how fast it is. I don't have an answer to prove, right? I have a goal, right? I don't know what to do. Is it n squared? Is it n cubed? I don't know. Here, right, it's somehow nice because it's like, well, I want to know what the performance of merge sort is. I want to start already knowing the answer. That's not realistic, okay? So typically what happens, right, is in practice, if you're doing this type of work, is you have an algorithm, you have no idea what it's supposed to be. Well, initially you have no idea what kind of the final result would be. But what you do is you look at it, right, and try to figure out, what does it seem like? Does it have loops that go here? Does it have recursion that goes here? You look at the structure of the algorithm and try to make some educated guesses about how it's put together, how it should run, right? And then maybe you pick a number, right? You say, okay, I think it's going to look like X, right? And then you're going to try and prove that. And either it works, in which case you're done, or at the very minimum, you'll learn more about your problem. You'll learn more about, this is my proof, this is where it failed, right? This is the step that went wrong because this isn't true, right? It tells you a little bit more, and you make another better informed guess of what it could be, right? And you try proving that one. You rinse and repeat until you understand enough about your problem that you make a good guess that is a guess that you can prove because it's not the guess, it's the right answer, okay? So that's typically what you do. Now, a lot of times people don't talk about that stuff just because it's like, well, we talk about the work in progress, right? A lot of proofs that are out there, if you go and look at them, they'll be like, oh, go A, B, C, D. You're like, okay, I don't have any idea how I'd get from A, B, C, D. Well, that's really because even though those may make sense logically, right, having seen them afterwards, probably they didn't occur to the author in that order. Usually they had to go A, B, C, F, right, and then they backtrack to A, C, or A, B, right? There was a kind of back and forth trying to figure out what would work and what would not work. Usually people just kind of exclude that work right from when they actually publish proofs because it's like, well, this is all the intermediate steps. But typically, right, you have to try a lot of stuff before you actually get to your real answer. All right, so having said that, let's kind of step forward and try to do this. So first I have my proof. So my proof technique here is direct construction. Okay, so I have different ways to prove things. I can use induction. Well, okay, induction is a general tool. I guess in terms of general proof techniques, right? Direct construction is one, right? So that's basically saying we're going to build our answer, right? We're going to just come up with it. Versus something like contradiction, right? Coming up with a counterexample. That's a slightly different flavor. Doing basically a counterexample-based proof here, contradiction-based proof won't work out here. It's a long story, but it won't work. Here we'll do direct construction, and things will be complicated, but they'll be bearable. All right, so let's start with this first definition. We're going to let C of n represent the number of comparisons necessary for an input of n elements. So this is kind of our base, well, not our base claim, but our base definition, right? So this is what we want to analyze. And we're hoping, right, that this C value, we can show that it matches up with this claim over here, right? The n log n claim, okay? So what do? Well, what we're going to end up doing is we have basically two steps. The first is we need to write some sort of a base case. Over here, I've called it a trivial case, right? This is also a base case. And then a recurrence, right? This algorithm merge sort is recursive, so they know when we write the growth function for it, it's going to be recursive. It's going to be a recurrence. So we want to try writing that out. On the right-hand side, I have just the source code. This is just a plain source code from the program. And we want to try writing out this base case and then the recursive step, right? This recurrence. All right. So looking at this, basically we want to start with some simple values for base case. One is basically n equals 0, and the other one is n equal 1. So n equals 0, basically what happens is your sorting algorithm just doesn't do anything. Okay. So these end up being equal, right? So if you have one element, right, you don't have to do anything. Right, you don't get down into anything else, right? You just are done. Actually, both of them for C equal 1 and C equals n, they'll actually, even though I have different notes on the slides here, they will actually both stop at this point here, okay? Because it's like, well, if I have an array, it has either one element or no elements, right? Those things are already sorted. I don't need to do any work. If I don't do any work, that means I don't have to do any comparisons, okay? So in this case, right, our C of 0 and C of 1 will both be equal to 0 because there's just no comparisons needed. All right, so that's kind of our base case, right? So these are our base cases. This is good, not too hard. Again, right, the idea is we want to know how many comparisons is required for this size of input. Just mainly think about the code. We realize, right, this return statement implies that I don't have to do anything, right, because it's not within the bounds. All right, so more complicated part here. So this is the recurrence, and there's an upper and lower one, okay? So somehow right, there's the idea of based on how many inputs I have, I may have a slightly different number of comparisons. What we want to do is basically characterize the worst case and the best case. So the most comparisons and the least comparisons, or an upper and lower bound. We're going to end up only proving one of these, but just for the sake of writing something that's really, really accurate, we're going to have both of them here. All right, so what do I do here? So we're reading these occurrences. C of n, right? So that's my C of n, right, is basically the exact number of occurrences of comparisons I need to sort this size of input. So that number, right, is going to be less than this stuff over here on the right-hand side. So what is the right-hand side stuff? So the number of comparisons I need to compare n, something of length n, it's going to be the number of comparisons, is going to be C of floor of n over 2 plus C of ceiling of n over 2. A lot of stuff happening here. First of all, right, you notice that we have that recursion there, right, C and C, right? So we're saying the number of comparisons necessary to compare is based on the sum of the number of comparisons to compare these smaller bits, right? So the smaller bits are n over 2 and n over 2, because that's the two parts of our array. Right, over here, right, we have this idea of doing this midpoint, right? And so we have basically n over 2 elements over here, n over 2 elements over here, okay? Because we're divided in half. And so if I want to know how many comparisons are required, I need to basically look at those two chunks. Because here, right, somehow what's happening is this is my C of n, right? It's measuring the number of comparisons for sort. And then sort, right, calls itself twice. And it calls itself twice in the smaller parts. The floor and ceiling things are basically just to make sure that rounding happens properly and we don't double count an element in the middle, right? Because an element is either in the first call or the second call. It can't be in both, okay? So just to get rid of the kind of numerical thing, we do ceiling on one and floor on the other. All right, so these two things here, again, correspond to these lines over here, right? These two sorts correspond to this over here and this over here. All right, so the last thing here, right, was to have n. So the n bit is actually coming from the call to merge. Okay, so what we're saying here is that kind of this worst case, right? This case of the most number of comparisons I could ever do, it's n. So it's n. Well, so it's basically what it's saying is we want to look at merge, or we want to figure out basically how many comparisons happen in merge. There's only one place we do comparisons. It's over here. This is less one. So we have to figure out how many times does less run. Right? That's the question we're asking. We need to figure that out for this one over here, right? N is the upper, and then n over 2 floor for lower. So we want to count out the number of times the less is called. And on this we can kind of just, we'll have to basically just conceptualize it. So basically what we want to think of is worst case is, so worst case, right, for this. What would cause less to be hit the most times? Well, less will be hit the most times when neither of the first two if conditions are true. So it should never be the case that I is greater than mid, J, or J is greater than high, right? I don't want either of those to hold. Rather, I want to make sure those are both false so that I get down to that third case. So what does that mean? Well, that's actually the equivalent of saying the following, that my arrays basically alternate. So this is maybe 2, 4, 6, 8. This is 1, 3, 5, 7. Because what we're saying here is that I never run out of one array early, right? That's what it's saying. Because I only use those top two cases when that array that I'm merging in runs out of elements. It's like, oh, I ran out, so I got to get some from the other one. Here, in order to make sure those never, or those are always skipped, we want to make sure that we're just alternating and we use up both arrays at the same time. And the way we get that is by having two arrays that basically have interleaved patterns. So every single time, right, I'll pick from one, then pick from the other, pick from one, pick from the other, pick from one, pick from the other. I'll not run either of them out early. So I'll have to keep on doing those comparisons, okay? So if I have perfectly interleaved arrays, that's going to maximize the chance that I call less, right? Less gets called every time I run inside this array, inside this loop, right? This is also, I guess, it's kind of an n-sized loop. It's maybe a little bit obscured because we have low and high, but n is basically referring to all the elements you're working with right now, and that's bound by low and high. So yeah, worst case, right, basically we need to have n elements. So that gives us our first recurrence over here. Okay, so we have the number of comparisons, right, is less than the number of comparisons to sort the left side plus the number of comparisons to sort the right side plus the cost to compare them when I have to compare every single element in the ones that I'm merging. All right, So what about the next one? The next one is structurally very similar. So the first part's all the same. What's different is that last term. So now my lower, it's basically saying, what's the cheapest I could do? The cheapest I could do, basically what we're saying is we want to hit this as few times as I can, which is implying that I want to hit the cases above it as many times as I can. Okay, so it's like I want to basically deplete one as soon as I can. Okay, so typically this case ends up looking like this. So this over here was the upper. The lower will look more like, I need space. Like this, things that are basically in order. So in this case, I'm going to keep on comparing. So I'm going to look at them, right? I'm going to compare the fronts. I'm going to take from the first one, then take from the first one, I'll have to go through and compare them all, and I'll end up taking from the first one. I'll need basically n over 2 comparisons to get rid of the first one, and then it'll be depleted, and I can just move the second ray to follow it, okay? So that basically, it's like this one's first, cost me comparisons, and this one afterwards, no comparisons needed. So length of this right is n over 2, and so that's what we get over here, n over 2. We basically just put that together with the stuff we have already talked about, and we get this full recurrence here. So there we have it. So we have 2 recurrences here, right? So this is basically for C, right? We have an upper bound and a lower bound. We're going to end up working with the upper one though, because like worst case is important, right? We want to know what is the most time we could ever spend on this. Okay, so we'll end up working with the upper bound. But we have these recurrence now. We have this idea of where the trivial base case is, and then we also have this idea of basically the 2 upper and lower bounds for how many comparisons are needed. Now, note right now that things are a little bit problematic for us because C is a recurrence, right? I don't really know what C looks like. So our next work, right, which is going to be kind of the main thing we do in this proof, is to find a closed loop solution to this. So I want one simple, hopefully, maybe polynomial formula, right, that can basically give me the runtime of this, right? Rather than having these recurrences where it's C expressed in terms of C, I want to have C just on one side. So that's what we'll take a look at in the next video. For now, I just kind of know this is our way we express the problem we want to solve, right? This is our growth function we've now written.